Hi, and welcome back. It's week 13 now. We're getting down to the wire here, getting down to the end. This probably be the last full lecture. Next week is going to be kind of a review, and we need to get that final taken care of. We're running out of semester. So uh, where we left off was compression test. We talked about that, and so let me get to the set of slides here. Next slide is the cylinder leakage test. So cylinder leakage. How do we do it? Well, first thing we do is we look at the bottom here in red, or, the question is, why would we do a cylinder leakage test? The answer is compression test failure. And I know I discussed this in the shop, but let's just talk about it again for a minute. A cylinder leakage test can be time consuming. It requires you to put the engine in specific positions for each cylinder. So if you have an engine that things are difficult to get to, you don't want to do a cylinder leakage test just for kicks. The best reason to do a cylinder leakage test is this. You've done a compression test and one or more cylinders have failed. If you've done a compression test and all the cylinders tested good, that would be like trying to find the leak on a tire that has good air pressure. If a tire has a leak, how are you going to know? The pressure is going to be low. If a cylinder has a leak, how are you going to know? The pressure is going to be low. So if it passes a compression test, you'd be looking for a leak that's not there. If it fails the compression test, now the question is, okay, we're losing pressure, where's it going? And there are really three major possibilities there. It's escaping through the intake valve back into the intake manifold, or it's escaping through the exhaust valve into the exhaust manifold. Excuse me. Or third possibility is it's escaping past the piston down into the crankcase. And if it's escaping past the piston, there's a couple possibilities there. You could have scored cylinder walls, so even brand new rings wouldn't be able to seal. You could have compression rings that have lost their tension from overheating or something like that, or they're stuck from carbon, or they're just worn. You could have, I've seen pistons with holes in them. So the pressure is going right through the top of the piston down into the crankcase. So what we're going to attempt to do with a cylinder leakage test is find out which direction the pressure is going. Is it going out the intake? Is it going out the exhaust? Or is it going into the crankcase? So let's take a look at that cylinder leakage tester for a minute. You're familiar with the cylinder leakage tester. We used it in the shop already. So this is just really review, nothing new. If I take the cover off this here, slide it out, and we'll get that back in frame. So two gauges on the leakage tester. There's the gauge that's the input pressure that comes in from the shop, and then the gauge that's actually in the cylinder. And so shop air is attached here. This comes out, shop air is attached there, and the other end goes to the cylinder. Put that back in. And then we have adapters that fit the cylinder. So notice these do not have a Schrader valve in them. And we talked about that, how the compression testers have that one-way check valve in them, but the cylinder leakage tester does not, because air has to be able to flow backwards through this hose into the cylinder, not just out. So the basic procedure here is to attach shop air to the fitting, and then we have an adjuster knob that allows us to set the air pressure on the input side. And the easiest way to do this is to set it to 100 psi, because we're looking at percentages when it comes to leakage. And so if we have this to 100 and the cylinder holds 90, it's going to show as a 10% leak. If it holds 80, it's going to show as a 20% leak. There are times, and we talked about this too, when you have a small engine where 100 psi applied on top of the piston causes the piston to be pushed down in the cylinder, which takes it out of the position it needs to be in for the cylinder leakage test. And if you remember, for cylinder leakage, we have to have the piston at top dead center on the compression stroke where both valves are closed, so the cylinder will be sealed up. If the piston gets pushed down in the cylinder, then it's no longer in that position. Air leaks out through one of the valves that's now open, and the test is useless. I've always been told that up to 10% leakage is absolutely normal. This gauge, the green, yellow, and red on this gauge are a little bit different. It has almost up to 40% in the green saying it's low. And then from 40 to about 70% says moderate, and anything over that is listed as high over here. So this is, you know, right here, this is 20, this is 40, 60. I'm telling you, if you have a cylinder with, you know, 35% leakage, that's not normal. So if I did a cylinder leakage test, even though that was in the green, if I'm much over 10, I'm going to start thinking I have some sort of a problem with that cylinder. So the way this gauge is labeled, I don't necessarily really care for, but the basic procedure, and we did it before, right, is you blow air into the cylinder at a set pressure. You see how much pressure the cylinder holds. There's always a little bit of leakage. Anything up to 10% is absolutely normal. A brand new engine would do that. Now, when you get above 10, it indicates you have some leakage, and if it's, you know, 20, 30, 40%, you've got a fair amount of leakage, and that could start affecting your compression, definitely. So back to the bit about the small engine. Sometimes 100 psi is too much, and so the piston gets pushed down. If that happens and there's no way to lock the crankshaft, what you may have to do is set your input gauge to 50 psi, and that means everything's cut in half on the other side. So zero leakage would then be 50 on the output side, right? And if you had 45, that would be 10% leakage. So we're at increments of 10. So this would be 0, that's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100% leakage. So if I was at 50 for my input PSI, that would be here. You know, here, if both needles were pointing straight up, I have 0% leakage. If this was 5 pounds off, you know, then I would say that's 10% leakage, 5 out of 50. So you wouldn't be able to go by these percentage numbers on the scale over here unless you're using 100 psi on the input side. So we used the tester. We've completed the test. We've blown air into each cylinder one at a time. And let's just talk a little bit more about that. How do you know when a cylinder is at top dead center on the compression stroke? Well, for cylinder number 1, there may be timing marks that you can look at on the front of the engine that allow you to know when cylinder number 1 is at top dead center. That will not tell you whether it's on the compression stroke or not. So another way you can possibly tell if a cylinder is on top dead center is to insert something physically into the cylinder, and you have to be careful with this. We demonstrated this. We put a long 1/4 inch extension through the spark plug hole and slowly turned the engine by hand, and we could see the extension rising as the piston, approached the top of the cylinder. And then you could tell when it stopped moving and started moving back downward, we had just gone over top dead center. So that's a way to tell that we're at top dead center. Now, how can you tell you're on a compression stroke? You could just try it. In other words, you're at top dead center, so blow air into the cylinder and see if it holds. And if it's 100% leakage, you're on the exhaust stroke, if it's all coming out the exhaust valve. But another way to do it is screw in the adapter and cover the end of the adapter with your thumb and start bumping the engine with the starter. And as the piston's coming up on a compression stroke, you're going to feel pressure building against your thumb. So you'll know it's on the way up on the compression stroke. Then you can remove that adapter and you can put your dial indicator or a screwdriver or that long extension like I showed you and finish turning the engine by hand to find top dead center. So the pressure building against your thumb tells you you're on the compression stroke. And then the physical, observation of something in the spark plug hole can tell you when you actually hit top dead center. Once you establish top dead center on cylinder number 1, you could just use math or use the degrees, right? So a 4-cylinder engine has a compression stroke every 180 degrees. So if your firing order is 1342, you've just completed your cylinder balance or cylinder leakage test on cylinder 1, you know the next cylinder is 3, and it's going to have a compression stroke exactly 180 degrees after cylinder 1. So 4-cylinder engine, it's every half a turn, every 180 degrees. So you could just turn the crank 180 and cylinder 3 would be ready to go. Another 180, cylinder 4, another 180, cylinder 2, and you're done. If it's a 6-cylinder, it's every 120 degrees. And an 8-cylinder is every 90 degrees. So that's one way to do it. You have to be really exact, though, turning the engine, counting, how many degrees. Half turn's pretty easy to figure out. Quarter turn, pretty easy to figure out. That 120 degrees can be tough. So you can get close that way, then maybe you want to verify top dead center with the method of using a screwdriver or a dial indicator or something to make sure you're right at the top. Okay, so I've done all the cylinders. How do we interpret the results? If we're here because of a compression test, really the cylinder we're going to be concentrating on is the cylinder that was low, the one that failed the compression test. If they're all low, that could be like we talked about with the compression test, that could be some sort of a valve timing issue or something like that. But one cylinder low, maybe it has a burned valve. Maybe it has a bent push rod that's not allowing the valve to close. Maybe valves are bent. We saw an engine in the shop this semester with all the exhaust valves bent, right? Maybe there's a problem with the piston or the rings. So how do you determine which it is? And that's really simple. You just listen for where the air is escaping. So if I have a stuck exhaust valve or a burned exhaust valve, when I do a cylinder leakage test, I'm going to hear air escaping at the tailpipe. If I have a burned or bent or stuck intake valve, I'm going to hear air escaping at the throttle body. When I put it in the cylinder, it's going to come out the throttle body. And if it's a lower end problem, rings or something with the piston, that air is going to get by into the crankcase, so I'm going to hear it at the oil fill cap. So it's really a simple mechanical thing, this cylinder leakage test. You're basically doing the same thing you do with a tire. You're blowing air in and seeing where it comes out. It's not really complicated. So let me just go back to the slides here a minute to make sure I didn't miss anything. So rotate engine to close both valves for the cylinder being tested. Check. Apply air with the tester set at 100 psi. Check. And we had that little discussion a minute ago that we might have a small little engine. If we're using 100 psi, then it's really easy math. Every pound is a percent. If we're using 50, every pound is 2%. So if we blow 50 in, and we've got 5, that's 10%, and I'm still 10% leakage. And like every other spec, if it was 11, would I say that's definitely the problem with the engine? Well, maybe not. That snap-on gauge allowed us 40, but I've done this test on a lot of good engines, just demoing it, and it's always less than 10 on engines that are running well. So take that for what it's worth. Here's an example of a test that was, I guess, more useful in the past. Not so much now, but timing advance. Years ago, and so if you're working on an older car, this might still apply. Especially, this was on distributor cars mostly. The timing advance, or which is electronic, could be disabled usually by unhooking some sort of a wire. So when you were going to hook a timing light up and check base timing on an engine, you had to disable the timing advance. So this test was designed to see if that timing advance system works. And so it's a really simple one. Following the manufacturer's procedures for disabling the timing advance, which is usually disconnecting an advance wire. You're watching with a timing light or with a scan tool, or even with your ears. When you disconnect that advance wire and it drops back to base timing, that'll be seen on a timing light. It'll be heard in an engine RPM drop, and it could be seen on a scan tool. And then when you reconnect that wire, the RPM recovers, the timing advances, and you may be able to see that on a scan tool. So this is a test that was more useful when the computer was telling the ignition module to advance the timing. It was verifying the communication between the two. Now the computer is completely in charge of when the spark plug fires, so this test has become kind of obsolete. I keep it in here because it's a reminder that retarded ignition timing, or timing that's not advancing properly, can cause two symptoms, and they are a lack of power and poor fuel economy. So if you have an engine that's exhibiting both of those symptoms, but otherwise running smoothly, we're not misfiring, stumbling, anything like that, there may be a problem with ignition timing. And depending on the vehicle, diagnosing that would be radically different. So most modern vehicles is completely controlled by the PCM, and there isn't really any way to test it. Next test, and this is why I kept all these for the end, is because they've been obsoleted by newer technology also, but you may not be working on newer technology, so this is a good thing to have in your toolbox. And I did this a demo in a lab, but cylinder balance test. If you suspect a weak cylinder, right? So you have a misfire, or it feels like a misfire. So you know that one cylinder is weak. You're trying to figure out which one. What do we do now? Now we look at the scan tool, we read the code. If cylinder 3 is misfiring, we got a P0303, cylinder 3 misfire, we know which one it is. There's nothing else to do. But if you're working on a car that's a little older, pre-96, doesn't have misfire detection, the only way of identifying the cylinder that's causing the problem is doing some sort of cylinder balance testing. So what we're doing here, right, is We're disabling one injector at a time and looking for an RPM drop. Now, one of the problems with doing that is, since the computer is now in charge of engine RPM, engine idle speed, when you disable that injector and the RPM drops, it's quite likely the computer is going to turn around and correct that RPM and bring it back to where it's supposed to be, even though you're missing one cylinder. So you may see this effect when you kill that injector. You may see an RPM drop for a short period of time, and then it recovers. So you got to watch right away. You just have to be aware that the computer can correct that low RPM. Some of the earlier cars, you could disable the computer-controlled, the idle air control valve. But now I'm going to say with electronic throttle bodies, there's really no way to disable that. So the computer is completely in control of the throttle body motion, and it has a target RPM it's looking for. And so anything that throws the engine off that target RPM, the computer is going to correct for and put it back where it wants it. So there'll be, besides a drop in RPM, you should notice definitely a noticeable roughness. And on a 4-cylinder engine, it's going to be more noticeable than it will be on an 8-cylinder, because you're killing 25% of the engine. So here's what you do, right? If you don't have misfire detection, disable one injector at a time. So since we have to stay generic here, I got to tell you, the easiest way to do that is to pull the electrical connector off the injector. Look for a drop in engine RPM. Cylinders that don't cause an RPM drop are not contributing. So if you pull an injector and it has no effect on the engine, it tells you that that cylinder wasn't doing anything in the first place. Killing it made no difference. It doesn't mean the problem is with the injector, but it means there's something wrong with that cylinder. No spark, no fuel, bad compression, and then the other tests, compression, cylinder balance, all that, those are designed to find out which of those it is, right? So this is just trying to identify a weak cylinder, which one is weak. What if you have direct injection? You're not going to be able to do this, right? You're not going to be able to pull the wires. You may not be able to even get to any kind of connector. You can coil unplug. You can disconnect the low voltage connector from that coil. It'll stop the coil firing. Same effect, that cylinder will stop operating, and there should be a noticeable RPM drop, at least temporarily, and there should be a noticeable decrease in idle quality. So this is, like I say, okay for older vehicles. It's okay for things that are not even cars. You might be working on something that's not a car. But on a modern vehicle, what are you looking for? You're looking for a misfire code. So I throw these things out here because I don't know what you're going to run into in the future. I know if you're working at a dealer, you'll probably never run into a vehicle you need to do this on. All you'll be doing, for the last 24 years, right, is looking at a misfire code. Okay, one more test in your toolbox. This is kind of no-code diagnosis stuff, right? If you don't have a code telling you exactly where to go, is the injector balance test. To really give you an idea of how this works, I have to demo it in the shop. But here's the essential, steps involved. Somehow pressurize the fuel rail. How do we pressurize the fuel rail? We talked about this with the fuel pressure testing. We cycle the key. So every time you turn the ignition on, you're going to get a 2-second prime. And the fuel rail, at some point, is going to reach its maximum, regulated pressure, say 50 or 60 psi, and then no matter how many times you cycle the key after that, it's not going to make a difference. So you got the fuel rail pressurized. You manually activate the injector. So we have a special tool that will connect directly to a fuel injector. right to the electrical connector. And with the push of a button, it'll fire that injector for, I believe it's 100 milliseconds. When that injector fires, you'll be able to see a pressure drop in the fuel rail as fuel flows out of the rail through that injector into the intake manifold. So the idea is you do this on every fuel injector and you compare the pressure drop on each injector with all the other injectors. Some things to be cautious of, right, is every time you fire that injector, you're putting liquid fuel directly into the intake manifold. You almost need to start the engine between every cylinder just to clear out all that fuel, or you'll be flooded. Or even worse, if you do one cylinder multiple times, you can actually hydrolock the engine. We had it happen. An instructor was doing a demo with the Ford scan tool, and the Ford scan tool just runs through, it automates it. It's kind of nice. It runs through and it fires each injector, and then it repressurizes the fuel rail, and then it fires the next injector, then it repressurizes and it fires the next injector, and it just runs through like an 8-cylinder engine in less than a minute. They're all done automatically. It controls the injector firing. And so the instructor was demonstrating this, but then did the demo and then had a student do it, and then had another student do it, and then had another student do it. And so every time this test runs, fuel is spraying out of the fuel injector into the engine. And what happened is, after several students did this test without running the engine, when they tried to start the vehicle, there was so much liquid fuel in the cylinders that it actually bent connecting rods. You can compress a gas, but you cannot compress a liquid. So that's known as a hydrolock. So it's not good. Anyhow, the idea here, right, is you start from the same pressure every time. So between cylinders, you need to repressurize the fuel rail. And the more accurate of a gauge you have, the more you're able to tell if all the cylinders are flowing the same amount. Why would you do this test? Well, if you had misfires, rough idle, which could indicate a leaky injector, hard start, excessive fuel trim correction. Right, so these are kind of potential fueling problems. So like I told you, some of the tests that we just talked about, you may not find much reason to do in this day and age because of the advanced diagnostics built into the PCM on the car. It can tell you, if there's a misfire, it'll tell you what cylinder it is. So you may never need to use some of these, but you might be working on older vehicles. I don't know, you might be working on a tractor, a boat, an airplane, and these things can come in handy. So now we've kind of reached that stage where we've talked about all the various diagnostics, maybe not everything that's possible, but most of the various diagnostics out there. And so now the question is, once we have identified the cause of a customer concern or the cause of a malfunction, now what do we do? Kind of an obvious answer, right? We fix it, but we don't just stop there. So let me talk about that a little bit. So I had it was an old Plymouth. They don't even make Plymouth anymore, but the vehicle had no heat. And I determined that the engine was not reaching operating temperature, and that's why there was no heat. You could see it on the temperature gauge on the dash. It just barely moved off of cold. The heater hoses didn't feel hot. So, if your heater hoses aren't even getting hot, the heater core is going to be cold. I don't care what you do with a blend door or anything, you're not going to get heat. So I was young, foolish. I went up to Kmart and I bought a thermostat, and I put the thermostat in and refilled the cooling system, bled it, and I'll be damned, still no heat. So I began to doubt my diagnosis and think, well, maybe there's something else. But then again, engine's not reaching operating temperature. There really isn't another explanation except for a bad thermostat, one that's stuck open. So back up to Kmart and got another thermostat, put that in, filled the system, bled it out. Same thing, no heat. Now I'm walking away from the job saying I don't know what to do. It has to be the thermostat. The engine's not getting hot. It's not like somebody installed an extra good cooling system, right? Everything else is the same on the car. It's all factory stuff, and the engine's not reaching operating temperature. There's only one possibility. It's the thermostat, right? So this time I went to a actual parts store and I bought, an actual better quality, better brand, spent a little bit more money, and put that in, and car had heat all day. Absolutely perfect. Fixed it. The problem was never the diagnosis. The diagnosis was correct right from the start. But the problem was that I was using crap parts, for lack of a better term. And so here's the thing, we all might be motivated to try to save money or to try to save our customers money. But if you're redoing a job 2 or 3 times, you're not saving anything. So you have to really be cautious about where you get your parts, the brand names you put in. I mean, I use Rock Auto and places like that all the time, get them online, but I buy part brands that I recognize, that it's the same thing you would get at a parts store. It's a brand that's been around forever and not just something that I've never heard of that happens to show up online somewhere. And sometimes the price is more, but I have confidence that when I'm done with the job's going to be done, right? So use quality parts. And then the other part, industry standard repair practices. I had some heater cores, that's just an example, a heater core, can be extremely difficult to replace. It means removing the entire instrument panel, the entire dashboard from the car, removing the heater box, getting it out on the bench, separating it, replacing the heater core, putting it all back together. And so I heard of a guy, just saying, well, I'm not going through all of that, and just hacked a hole in that heater box, changed the heater core, and then slapped the heater box back together with some JB Weld or super glue or something. And my thought was this: that's not your car. You don't have the right to hack it apart like that. When somebody brings a car to you, they have a right to expect that the repairs you do are going to be up to published procedures that the manufacturer has recommended and approved. Does that mean the shop manual is always absolutely correct on every step you need to take? No, I don't think it does. I've seen some pretty stupid things in shop manuals where they have you doing absolutely unnecessary steps. But the thing about the shop manual is it's almost like a legal document, right? If you follow what's in the shop manual and an attorney were ever to ask you, why did you do what you did? If you can point to the shop manual and say, because the shop manual said so, then you have nothing to worry about. That's your defense, right? That same attorney says to you, why did you do what you did? And brings up the shop manual and says, why didn't you do this? And you said, well, I didn't feel like doing that, or I thought my way was better. That's kind of indefensible, right? You had clear instructions of industry approved procedures and you went off on your own. And so you're taking that responsibility now on yourself. So just be aware of that. I know you're not always going to do things absolutely by the book, every single step. You know it, I know it. I've been around long enough to see it. But people that are good at this, they stay pretty close to the shop manual, and they don't have comebacks. They don't have failures. They know the sorts of things not to do, the shortcuts not to take, and that can take years of experience. So it's always at least safe to follow the shop manual procedure. That's why we try to teach it here. Before you do a job, bring up all data, bring up the procedure, follow that. Is it absolutely the fastest way? Not necessarily. Is it the best way? Maybe not. Is it an acceptable way that is going to keep you out of trouble? Well, it should be, right? So leave the hack jobs for the beer swilling backyard guys. And you want to do this in a professional manner, the repair, and work within industry standard repair procedures. So now you've done the repair, now what? Do we ship it, hand it back to the customer, hope everything went okay? Probably not the best way of handling things. So always within whatever you're capable of doing, however you can do this, something else you want to do is verify the repair. So let's take a look here. So we've done the repair. We want to verify and retest. So let me stop my video here. There we go. So we want to verify and retest. If we had codes, diagnostic trouble codes, we want to verify that they've been cleared. In most cases, a road test is called for. Verify the symptoms are gone, and to verify the code doesn't come right back. Now, obviously, some of these things, like, well, I'll give you an example, an evap code, small leak, large leak, that can be kind of difficult to verify or repair on a road test. Reason being, getting that evap monitor to run probably involves an overnight cold soak and then some driving. So it may not be practical for something like that to absolutely verify the repair before returning the vehicle back to the customer. So in that case, that should be explained to the customer that the monitor won't run until the vehicle sits, and I'm sure they don't want to leave the car for a week so you can go through and make sure all the monitors have run. But for other things like misfires or lack of performance or stalling or idle quality problems, etc., if you were able to verify that the condition existed before you did your diagnosis and repair, you should be able to verify that the condition does not exist after you've done your repair. But here's one caveat, one thing you have to keep in mind. Some symptoms only show up when the engine's cold. Some symptoms only show up under load. Some symptoms only show up when the engine's hot. Maybe on a cold day, maybe when it's raining out, I don't know. But in next semester's class, we're going to talk about the term similar conditions and what it officially means for OBD2, the terminology. But essentially, it's the same temperature and load conditions that existed when you first verified the concern. So if the problem's at idle, you're going to verify the repair at idle. If you verified the symptom at wide open throttle, you're going to verify the repair at wide open throttle. If it only happens on a cold engine, obviously you want to make sure that it no longer happens on a cold engine. So the road test has to be under similar conditions. And then recheck to make sure they didn't return. You can't just go on the malfunction indicator light, because some or a lot of codes nowadays take 2 failures before they'll actually illuminate the malfunction indicator light, the check engine light. And they won't set a code, a current code. What they'll set is a pending diagnostic trouble code, meaning that the monitor's failed once, but it's a 2-trip monitor. It has to fail twice to set a code and turn on the light. So if you do the road test and then verify that you don't have any even pending codes, then you know the problem didn't recur, at least during that road test. Very important. So that about does it for this week. Next week, we'll spend a little bit of time talking about forced induction, and then we kind of got to wrap things up and get the final going. So there's not a whole lot more material to cover for this semester. Obviously, everything that I've talked about, every video I've done, every slide we've used, every video that I found on YouTube and showed for you guys is all still here on Blackboard. So for review purposes, you can rewatch the entire semester if you want. But I think that's a little impractical. So if you really want to review, think about what was on those first 2 tests. And I will do a review session before I put the final out there and have you take it. So we'll see you in lab. Today is Monday. We have the first lab tonight in a couple of weeks, and hopefully we'll get some stuff done. And the rest, if the ones that I don't see, that probably by the time this video makes it online, that will be over. So you Monday night people, email me, whatever, call me. The rest of you, I'm there, Tuesday, Wednesday, in person if you have questions, and available by email or phone the rest of the time. Phone, you'll have to leave a message, but I will call you back. So that's about it. I'll see you in the shop.